As you are all aware about ozone, today we will discuss about the preparation, properties, structure and uses of ozone. Myself Dr. Digna Varghese. Let me start with some general information on ozone. Ozone has two properties of interest to human health. First, it absorbs UV light, reducing human exposure to harmful UV radiation that causes skin cancer and cataracts. Second, when inhaled, it reacts chemically with many biological molecules in the respiratory tract, leading to a number of adverse health effects. Contents of today's presentation is ozone, preparation of ozone, properties of ozone, structure of ozone, and uses of ozone. Ozone. The name ozone derives from ozone, the Greek verb for smell, referring to the ozone's distinctive smell. We know ozone or trioxide is an inorganic molecule with the chemical formula O3. It is a pale blue gas with a distinctively pungent smell. So the name ozone derives from the Greek verb ozone for smell. It is an allotrope of oxygen. Ozone is formed from the dioxygen by the action of ultraviolet light and electrical discharges within the Earth's atmosphere. The highest concentration of ozone layer on the stratosphere, which absorbs most of the sun's ultraviolet radiation. It is preventing from the damaging UV light reaching the Earth's surface. Ozone is a powerful oxidant and has many industrial and consumer applications related to oxidation. In 1785, the Dutch chemist Martinus van Merum was conducting experiments involving electrical sparking above water when he noticed the unusual smell, but he failing to realize that he had in fact created ozone. Martinus van Merum was a Dutch chemist. A half-century later, Christian Frederick Schonbein noticed the same pungent odor and recognized it as the smell often following a bolt of lightning. In 1839, he succeeded in isolating the gaseous chemical and named it as ozone. The ozone layer or ozone shield is a region of Earth's stratosphere that absorbs most of the sun's UV ultraviolet radiation. It contains high concentration of ozone in relation to other parts of the atmosphere, although still small in relation to other gases in the stratosphere. The ozone layer contains less than 10 parts per million of ozone, while the average ozone concentration in Earth's atmosphere as a whole is about 0.3 parts per million. The ozone layer is mainly found in the lower portion of the stratosphere, from approximately 15 to 35 kilometers above Earth, although its thickness varies seasonally and geographically. Now we are moving to the preparation of ozone. Prepare ozone by passing silent electric discharge through dry, unadulterated and cold oxygen in an extraordinary device. This device is what we know as the ozonizer. When a silent electric discharge is passed through the pure dry oxygen, the ozone is formed. The reaction is initiated by a sparkless or silent electric discharge to produce less heat. Oxygen is never converted into ozone completely. 10% of oxygen is converted to ozone, and we always obtain a mixture of oxygen and ozone. This mixture is called ozonized oxygen. Preparation of ozone is done by using a silent electric discharge in a specialized device known as Siemens ozonizer or ozonizer. When a silent electrical discharge is passed through a pure dry oxygen, the ozone is formed. The fully or completed oxygen is not converted into ozone. Only 10% of oxygen is converted into ozone, and here at the end of the reaction we will get a mixture of ozone and oxygen. So this air is known as, or this mixture is known as, ozonized oxygen or ozonized air. The formation of ozone from oxygen is an endothermic reaction. Enthalpy value is plus 284.5 kJ per mole. We know an endothermic reactions are chemical reactions in which the reactants absorbs heat energy from the surroundings to form the products. These reactions lower the temperature of their surrounding area, thereby creating a cooling effect. It is necessary to use such a reaction, a silent electric discharge, to prevent decomposition of ozone. If high electric discharge is used, ozone is decomposed, but here we are using a silent electric discharge to prevent the decomposition of ozone. What are the precautions to be taken for the preparation of ozone? First one is pure and dry oxygen should be used. That means the reactant is pure. The ozonizer should be perfectly dry. There is no water or moisture content or any other impurities present in the ozonizer. A fairly low temperature should be maintained because it's an endothermic reaction. There should be no sparking. If high sparking occurs, the product formed will be decomposed to some other products. Now the next step in the process of preparation of ozone is the isolation of pure ozone. It is by fractional distillation method. We know when silent electric discharge applied to the reactants in an ozonizer, that only 10% of the oxygen is converted into ozone. So we will get from the ozonizer as ozonized oxygen. So we have to isolate pure ozone from that mixture. This is done by fractional distillation method. Pure ozone can be obtained by fractional distillation of oxygen-ozone mixtures, and the ozone can be condensed to a deep blue, highly explosive liquid. This is not a reaction for the faint-hearted, as it is notoriously temperamental and explosions occur readily and without warning. So there should be some care when we are performing such a reaction. We know the boiling point of ozone is minus 112 degrees Celsius, while that for oxygen is about minus 182.5 degrees Celsius. For this reason, we can use for the separation of ozone from oxygen by fractional distillation method. When ozonized oxygen is cooled in liquid air, ozone condenses to a liquid at minus 112 degrees Celsius to a deep blue liquid, while oxygen does not condense at that particular temperature. Some oxygen that gets dissolved in liquid ozone then separated and removed by fractional distillation. So we will get at the end of the fractional distillation the pure ozone. Commercial preparation of ozone. We are using for the typical conversion of oxygen into ozone by Siemen Halske ozonizer. Here this ozonizer consists of a battery of glass or porcelain tubes with the internal tubes of aluminium, which is enclosed in an earthed iron tank of water to cool the apparatus. The aluminium tubes are charged to a potential of about 8000 to 10,000 volts, and here each battery of 6 to 8 tubes requiring half a kilowatt of power. The ozone air apparatus consists of two sheets of aluminium goes by a plate of insulator, several units being enclosed in a case, and alternate plates are charged and earthed. That is, here the aluminium tubes are enclosed in an earthed iron tank, and the aluminium tubes are cooled by water in the compartments. The best prediction amounts to about 40 to 60 gram of ozone per kilowatt hour at a concentration of 2 gram of ozone per cubic meter of air. With pure oxygen, 120 to 180 gram are obtained. So there is a preparation of the ozone. There should be the reactant is highly pure. Then only the conversion of oxygen to ozone is higher. The yields are about 5 to 15% of the theoretical with air and oxygen respectively. With air only conversion 5%, with oxygen, pure oxygen, 50% conversion occurs. Here we can see from the figure that it is a Siemen Halske ozonizer. It consists of the cast iron box, which contains a vertically fixed aluminium rods. These are the aluminium rods which are vertically fixed to the cast iron box and which are enclosed in a glass separately in a glass cylinders. And the box is divided into three compartments, three horizontal compartments. First compartment is this, that is the lower compartment, that is represented as A, and the second one is, that is the middle compartment, represented as B compartment, and the upper compartment is C compartment. So the cast iron box horizontally divided into three compartments, A, B and C. The water is passed through the B compartment, that is the second or middle compartment of the cast iron box, and the water is passed through here in between the aluminium rods, which is placed in a glass cylinders. And what is the reason to fill the water here? In order to cool the apparatus. Each aluminium rod rests on a glass plate. Each aluminium rod is rest on a glass plate. These are the aluminium rods which are not directly attached to the or fixed to the cast iron box. It is fixed on the glass plate which is placed at the lower A compartment, and by this the aluminium rod is insulated from the iron box. That means aluminium rod is not directly fixed to the iron box, but it is placed on the glass plate at the A compartment. That means the aluminium rod is insulated from the iron box. Air entering from the bottom compartment. That means here the air is the reactant. If it is not air, pure oxygen can be taken. That is enter the lower compartment A, and is passes up through the annular space between the aluminum rods and the surrounding the glass cylinders. Here the oxygen or air can be moved to the upper compartment C, and here also the oxygen or reactant air can be moved to the upper compartment, and here also the annular space through which the oxygen or air can be moved up, and this way the oxygen can also move to the upper compartment. Here a high potential of 8000 to 10,000 or 10,000 to 40,000, a high potential is applied to the rods so that the air comes out of the cylinder. At the top compartment C can be a mixture of oxygen and ozone. Here the air is come out from the apparatus through this way, that is from the upper part of the compartment, that is ozonized air, that is a mixture of oxygen and ozone. Only 10% of the oxygen is converted into ozone. If we are taking pure oxygen, 15% of the oxygen conversion takes place. If you are taking air as the reactant, only 5% of oxygen converted to ozone. So I will explain again. First once again I will explain this. The iron box contains cast iron box here, and which contains 2 aluminum rods, which is kept in a compartment, and which is placed on the glass plate. Thus it is insulated from the iron box, and water is filled in the B compartment in order to cool the apparatus, and in the C compartment there is an electric potential is applied, and the air is passed from the lower part of the compartment, that is A, and it is passed up to the annular space given in between the glass cylinder and the aluminum rods, and which is passes up, and the electrical potential is applied to this air or oxygen. The ozone is converted, oxygen to ozone is converts, and which is collected through the upper part of the or the exit part of the cast iron box. If we take air as the reactant, only 5% oxygen is converted into ozone. If we take pure oxygen as the reactant, only 15% of oxygen is converted to ozone. So we usually get a mixture of oxygen and ozone, that is ozonized oxygen or ozonized air. Another ozonizer can be also used for the production of ozone, that is Brodie's ozonizer. It is similar to Siemen's ozonizer, but here the dilute sulfuric acid replaces the tin foil in the Siemen's ozonizer. 2 carbon electrons are dipped in the acid and connected to an induction coil. A current of dry oxygen is passed through the space between the tubes. The ozonized oxygen containing about 5% of ozone comes out at the other end. If the apparatus is kept cool by water, the proportion of ozone may go up to 20 to 25% from 5%. Another methods also can be used for the preparation of ozone, that is electrolysis of water and also the thermal treatment of oxygen. And structure of ozone. According to the experimental evidence from the microwave spectroscopy, ozone has a bent or angular molecule. Ozone is a bent or angular molecule with C2V symmetry, that is similar to the water molecule, and the oxygen distance are 128 picometer, that is 1.28 angstrom, and the oxygen bond angle is about 116.78 degree. The central oxygen atom is sp2 hybridized with a lone pair of electrons, and ozone is a polar molecule with a dipole moment of 0.53 dpi. The molecule can be represented as a resonance hybrid of the two contributing structures, each with a single bond on one side and a double bond on other side. The arrangement possesses an overall bond order of 1.5 for both sides. So the structure of the ozone is a bent or angular molecule. The oxygen distance is 1.2 angstrom, and the oxygen bond angle is 116.78 degree, and the central atom is sp2 hybridized and with one lone pair of electrons, and the ozone is a polar molecule with a dipole moment 0.53 dpi, and it possesses a resonance structure, and it has a bond order of 1.5, and it is isoelectronic with nitrate ion. Physical properties of ozone. Ozone is a colorless or pale blue gas. It is slightly soluble in water and much more soluble in inert non-polar solvents such as carbon tetrachloride or fluorocarbons, in which it forms a blue solution. At 161 Kelvin, it condenses to form a dark blue liquid. It is dangerous to allow this liquid to warm to its boiling point, because both concentrated gaseous ozone and liquid ozone can detonate. At temperatures below 80 Kelvin, it forms a violet-black solid. Most people can detect about 0.01 micromole per mole of ozone in air, where it has a very specific sharp odor, somewhat resembling chlorine bleach. Exposure of 0.1 to 1 micromole per mole produces headaches, nausea, burning eyes, and irritation to the respiratory passages. Even low concentration of ozone in air are very destructive to organic materials such as latex, plastics, and animal lung tissue. Ozone is diamagnetic with all its electrons paired. In contrast, oxygen is paramagnetic, containing two unpaired electrons. Chemical properties of ozone. First chemical property of ozone is its decomposition. Second one is oxidizing action. In that, action with metals, action with non-metals, action with metalloids, action with compounds with evolution of oxygen, action with compounds without the evolution of oxygen, and its bleaching action. These are some reactions that related to its oxidizing action. Next reaction or chemical property is action with peroxides and addition to unsaturated compounds, in that it forms an ozonide. First chemical property is its decomposition reactions. Ozone is thermodynamically unstable with respect to oxygen, and it decomposes to oxygen slowly, that is, ozone decomposes to oxygen. In this decomposition, although it is a slow process, but it is spontaneous, as it results in the liberation of heat, that is, its delta H value is negative, and an increase in entropy, that is, delta S is positive. And so the ozone in decomposition reaction is quite rapid upon heating or in the presence of a catalyst like manganese dioxide or platinum, or copper oxide, it is rapidly converted to oxygen. Oxidizing action. Due to the ease with which it decomposes and liberating atoms of nascent oxygen, that is, ozone decomposes to give oxygen and nascent oxygen, this oxygen responsible for its oxidizing action. So ozone acts as a powerful oxidizing agent. First reaction is action with metals. That is, ozone will oxidize most metals except gold, platinum and iridium to oxidizes the metals in their highest oxidation state. First reaction is action with mercury on ozone and forming mercurous oxide and mercury 1 oxide. Mercury oxidized from 0 to +1 in mercurous oxide, that is tailing of mercury. As a result, mercury loses its mobility when exposed to ozone and sticks to glasses and leaving tails. This is called tailing of mercury. Another action with metals is with silver. Silver reacts with ozone to form silver oxide, and here also silver is in the +1 oxidation state. Next reaction is action with non-metals. Ozone oxidizes non-metals like sulfur, phosphorus and iodine to the corresponding oxo acids. Ozone oxidizes sulfur to sulfuric acid. Here sulfur oxidized by ozone to sulfuric acid, and phosphorus oxidized to phosphoric acid, and iodine oxidized to iodic acids. Action with metalloids. Ozone oxidizes metalloids like arsenic and antimony to the corresponding oxo acids. That is, arsenic converted to arsenic acid H3AsO4, and antimony converts to antimonic acid H3SbO4. Next reaction is action with compounds with the evolution of oxygen. Ozone oxidizes copper sulfide, zinc sulfide and cadmium sulfide to the corresponding sulfides. That is, metal sulfides reacts with ozone to give corresponding metal sulfides and the evolution of oxygen. And here the metal can be lead or copper or zinc or cadmium. If lead sulfide reacts with ozone, lead sulfate with oxygen. If copper reacts with ozone, copper sulfate with oxygen. Zinc reacts with ozone, giving zinc sulfate with oxygen. And if cadmium reacts with ozone to give cadmium sulfate with the evolution of oxygen. Second reaction is when ozone oxidizes ferrous to ferric. Here ferrous sulfate reacts with the ozone in presence of sulfuric acid, giving ferric sulfate Fe2+ converted to Fe3+. This with the evolution of oxygen. Another reaction is potassium nitrites reacts with ozone to give nitrate with the evolution of oxygen. Ozone oxidizes iodide. Here I- to iodine. In this, oxidation state of iodine is 0. So -1 to 0, increase of oxidation state, therefore oxidation. Iodide oxidized to iodine with the evolution of oxygen. This is a method used for the quantitative method for estimation of ozone gas. The iodine liberated here can be titrated against a standard solution of sodium thiosulfate. We can estimate the amount of ozone gas by this method. So it is used as a quantitative method for estimating ozone. Ozone oxidizes halogen acids to the corresponding halogens. That is, generally we can represent as halogen acid as HX, which reacts with ozone to give halogen X2. If it is HCl, reacts with ozone to give oxygen with chlorine with water. Potassium ferrocyanide reacts with ozone. It oxidizes potassium ferrocyanide to potassium ferricyanide, and here Fe2 plus to Fe3 plus. Potassium permanganate, ozone oxidizes potassium permanganate to potassium manganate to potassium permanganate. Here the oxidation state of manganese is plus 6 to plus 7. So potassium manganate is oxidized to potassium permanganate by ozone with the evolution of oxygen. Next reaction is its bleaching action, that is an oxidizing action of ozone. If colored matter reacts with ozone to give colorless oxidized matter with the evolution of oxygen, this is responsible for its bleaching action. Like chlorine. Action with compounds without the evolution of oxygen. In this reaction, there is no production of oxygen or evolution of oxygen occurs. When we treated with stannous chloride, reacts with ozone in presence of concentrated hydrochloric acid giving stannic chloride. Here stannous means plus 2 is its oxidation state, here plus 4. So tin is oxidized from plus 2 to plus 4 by ozone without the evolution of oxygen. Another reaction is sulfur dioxide is oxidized by ozone to give sulfur trioxide. Next reaction is action with peroxides. Ozone reacts with peroxides, example hydrogen peroxide and barium peroxide, bringing about their reduction to the corresponding monoxides. Here hydrogen peroxide reacts with ozone to forming water. Here the hydrogen reacts with oxygen to form its monoxide like water. So ozone reduces the hydrogen peroxide to water and barium peroxide to corresponding its monoxide, that is barium oxide, by the action with ozone. Next reaction is addition to unsaturated compounds. It's ozonide formation. Ozone adds to organic unsaturated compounds to yielding corresponding ozonides. In an inert solvent like carbon tetrachloride at a very low temperature reaction condition, ozone adds to alkenes across the double bond and breaking both the bonds and form an ozonide here, and which undergo reductive hydrolysis by the presence of zinc, forming ozonide breaks and forming aldehydes or ketones. Here forming ketones. The breaking of bond occurs like this. Here R1 R2 C double bond O, one ketone, and here R3 R4 double bond C double bond O, another ketone, and also we are getting hydrogen peroxide, and when we adding ozone to the alkene in an inert solvent, carbon tetrachloride at very low temperature, giving breaking of bond occurs and formation of ozonide, which on reductive hydrolysis giving ketone or aldehyde depending upon the alkene used. Another reaction under similar conditions, ozone adds to alkynes, also yields to the corresponding ozonides. Here ozone adds to alkynes to give corresponding ozonides, and which undergo hydrolysis with zinc dust, that is reductive hydrolysis, and water yields dicarbonyl compounds, that is the product formed here, and it undergo oxidative cleavage to a mixture of carboxylic acid and by hydrogen peroxide formed by the reaction. So when an alkane undergo reaction with ozone, it forms first ozonide and then it undergo reductive hydrolysis to give dicarbonyl compound, which in turn undergo oxidative cleavage by to a mixture of carboxylic acid. These are some important chemical properties of ozone. Uses of ozone. Ozone is used as a germicide, a substance or other agent which destroys harmful microorganisms, that is known as germicide. Ozone is used as a germicide, and ozone is used as a disinfectant. Disinfectant means it can destroy the microorganisms like bacteria. The ozone versus coronavirus, that is ozone's efficacy as a virucidal in disinfectant. So ozone is used as a disinfectant to clean the surface. For purification of air in tunnels, it is also used for the purification of air in tunnels, theatres, underground railway station, and other enclosed crowded places. So ozone is also used for the purification of air in where it can be used as enclosed crowded places. It is also used in the manufacture of potassium permanganate, and it also used for ozonolysis for detecting the position of multiple bonds in unsaturated compounds as well as in the production of carbonyl compounds. For destroying stenches in slaughterhouses, that is foul smell in slaughterhouses, kitchens and cold storage rooms. For bleaching oils, it is also used for bleaching oils, ivory, flour, starch, pulp and textile fibers. It also, the most important application of ozone is it's in the form of ozone layer. It protects us from the harmful UV rays of the sun. These are some important applications of ozone. Thank you for listening me.